You have your mic.
Okay, I'll try that. Okay, cool. Good morning, everyone. This is Shekhar Berry, and I have with me Elvir, Kuric. We work for performance and scale engineering. And our topic of discussion for today is performance and scalability of CNS 3.6 in an OpenShift container platform using brick multiplexing. So let's go over the contents for today. So we'll first give you a brief introduction. Thank you, Michael, for providing an introduction of what is CNS, what is OCP, and what is persistent volume. This is very helpful. And then we'll go about and explain what is brick multiplexing, performance, and then we'll tell you about the performance analysis, scalability analysis, next steps, what we are trying to do, and finally the conclusion. What's happening? Is it loose? Yeah. Cable is probably loose. I'm just.
Is this one up? No.
No.
Got some troubles with this cable. Just a second.
It was working, but
Yeah.
don't push it hard.
Okay.
And there's a problem with VTA with the input.
Sorry for that. Okay, so where we are, so just a brief introduction. What is OCP? It's a terminology which we are going to use in future slides. So OCP, as you know, it stands for OpenShift Content Platform. Is an application platform or PaaS. Is basically Kubernetes plus some add-ons. Some add-ons means we have Ansible-based installation, some web interfaces which will help us to see the GUI properly, and then rel-based. Everything is rel-based. What is CNS? CNS, as Michael explained, is container native storage, and it's basically the way to run cluster inside containers. Okay, so what was the motivation for this test? So I should probably step down. It's better to see it from here. Is it okay, Nigel? Yeah. Okay, sure. So brick multiplexing feature introduced a lot of advantages in terms of memory consumption. So we tried to figure out whether is there any performance degradation with brick multiplexing. We tried to compare the performance between brick multiplexing enabled and brick multiplexing disabled, and just to find out how much we can scale with brick multiplex enabled. So, and what are the resource constraints when we scale to a high number, say beyond 500 volumes or more than that. So we'll show you all of that. So what is brick multiplexing? So all storage in cluster is managed by bricks, which is just directories on servers. So the consistency of volumes across all the bricks is managed by cluster FSD, which is what consumes memory. So in older releases, oh God. This cable is probably loose. Okay, just back, cool. So in older releases of cluster FS, it won't allow me to proceed now.
There's a problem with the output of use this. Don't not to touch. This is better. You can see left, right.
Okay. Okay. Yeah, this is much better. So in older releases of cluster FS, there was one process per brick per host for a brick. So, but with brick multiplexing, only one cluster FSD process is governing the bricks, such that the amount of memory consumed by cluster FS pod is drastically reduced, and we can scale further. So, what was the resource constraints before brick multiplexing? The resource constraints were in ports, memory, and CPU. In ports, scaling for 100 of bricks requires 100 of ports, which resulted in a lot of firewall contention. Whereas for memory, some data structures in cluster FS are global, while some data structures are associated with translators in the brick. So replicating this global data structures across 100 of bricks was consuming a lot of memory. And for CPU, just like some data structures in memory, we have some global pool of threads, which consumes a lot of global threads, and that results in a lot of context switching. So with brick multiplexing, we are now consuming one port, one set of global data, and one set of global pool of threads, reducing resource consumption and contention. Okay, before we move on to performance analysis, I just want to discuss the use case where this brick multiplexing would be beneficial. So cluster traditionally has a scale-out distributed architecture where we used to use one large volume across different servers. But now, contrary to this, in CNS environment, what can happen is we can have large number of volumes which are packed densely inside, say, 3-node architecture. So there, we'll see the benefits of brick multiplexing, how it is performing, how it's helping us, how there is no performance degradation, or how it's performing in terms of scalability, how it's helping us to scale. So in the performance analysis, our test environment involved 8 nodes, 3 of which were dedicated nodes for CNS, and 5 of them were application nodes, including master. There were 48 gig of RAM on at least each of the CNS nodes, and there were 12 hard drives of 1 terabyte capacity, giving us a total capacity of 12 terabyte. And there were 10 gig link for data and 1 gig for management. And we used cluster FS 3.8.44, and this was run on OCP 3.6. So what was the test procedure? So persistent volumes were scaled from 100, 200, 300 to 1000, and tests were run on it using pbench FIO. The tests were reproduced, we repeated the test so that we get reproducible numbers. And then performance comparison was done between brick multiplexing enabled and disabled environment, just to make sure that there is no performance degradation between them. So this is the graph which shows us the scalability performance when we scale the volumes, persistent volumes from 100 to 1000. So as you see, the performance is between here, if you notice here, this is for 100 volumes and this is for 1000 volumes. So the performance is actually double for sequential write from going from 100 to 1000. This is because with Hecate, what we have seen is we haven't seen a homogeneous distribution of volumes across the bricks. So although there were 12 bricks per node, giving us 36 drives in total, in case of 100 volumes, only one brick was being used in the backend, or maybe 70% of the brick was used in the backend, whereas 20% of the volumes were on the different bricks. So this is what limited the performance here, but this improved drastically when we moved to 1000 because more number of bricks were being used or hard drives were being used in the backend, and that resulted in a better performance. Whereas for reads, we saw performance close to line speed, and read-write performance were in between these two, which was as expected. One interesting thing to note here is we are running I/O concurrently on 1000 nodes, 1000 persistent volumes in a 3-node CNS environment, which speaks a lot about clusters' reliability at this scale. So this is just for capturing this data, but we also did run IOs for whole night for 48, excuse me, for 48 hours without it breaking. So that speaks a lot. So this is the performance comparison between brick multiplexing on and off. As you see, there's hardly anything to choose in between, so that, excuse me for my throat, it's really bad today. So you see there's no performance degradation with brick multiplexing on, and that speaks a lot about brick multiplexing as a feature. So with this, I'll ask Elvir to please come up.
Thank you.
Yeah.
So, I hope I'm not going to spoil this water. Okay. So, in the second part of our test, we were running the scalability. So, it was necessary to say how many volumes we can create in the desired time, and how much it takes for these volumes to be created. And the problem was Kubernetes. So this slide is about how it was before the Kubernetes time with the cluster usage. And the thing is that prior to Kubernetes, a user will create one volume, export it to the actually, the storage administrator will create one volume and export it to the other users. And the change in that volume will not be performed for a long time, maybe weeks, days. Now it's completely different. Now OpenShift users are in position to create many persistent volume claims. That means volumes in very short time, and to destroy them in very short time. So we wanted to know how long it takes to create, for example, different number of persistent volume claims on the top of CNS, and we tested different configurations, but you will see results for 1,000 CNS volumes. Actually, 1,000 persistent volume claims when bounded using dynamic provisioning from the Kubernetes side, and then create them. Configuration was OpenShift 3.7. That is the latest Kubernetes beats in the part of OpenShift, and on the top of RHEL 7.5 and 7.4, and with the latest Heketi images. A bit about testing. We have a tool which is calling cluster loader. That is a tool which says, okay, create X number of projects, put their epsilon number of pods, and schedule them across the OpenShift cluster or Kubernetes cluster. The second tool is pbench, which is actually getting us the stats how busy are OpenShift nodes during the test execution. So when the test starts, we start pbench tools, which is actually collecting system data for all machines we want, and show us system usage, CPU, memory, and many other parameters. And the third tool which I use is a Heketi volume monitor, a small script which I created in order to get a number of Heketi volumes, how they appear on the Heketi API. So Heketi API / volumes. So the number is from there, how many Heketi volumes is present. So this is the first part, this is brick multiplexing. So prior to brick multiplexing, you can see on the first here line, it says for 1,000 CNS volumes or 1,000 Heketi volumes, it was consuming around 30 gigabytes of memory per OpenShift node. That means where CNS pod was scheduled. When brick multiplexing is on, what is the case in the latest images and the latest code, the memory consumption is reduced, and that is helping us to scale more persistent volume claims with the less memory, smaller memory footprint. The first two, brick multiplexing on and brick multiplexing off, just persistent volume is created and brought to the state when it is bound. And the third one, you can see small memory increase. It is the that is the test where the persistent volume claim was actually mounted inside the pod. So there is also that mount operation present. That is actually the most reflecting state. Pods were just simple pods, so nothing special, because that was not the point of the testing. It was important for us to get info how storage is reacting, and we were not looking at the application start time because that is other side. Yes, please.
So were the pods mounted, the volume running on the same nodes as the cluster? Or
No. Different nodes.
Then I would have assumed that
The memory stat is from the OpenShift nodes, where the CNS pods are present.
no other applications.
No other applications. That is how I'm doing, because I strongly believe that CNS pods are not just another pods in the OpenShift or Kubernetes. I think they should get a bit more attention, and they are more important. So that's the reason why I'm putting them separately on the nodes. But other people have different opinion. Okay, so if you send a request to create, for example, different number of persistent volume claims, for us it was interesting to see how fast user can expect to get, for example, 100, 300, 500, 1,000 persistent volume claims. And this is the bound state. That means without mount. In the next graph, I will show you with the mount state. So to create 1,000 persistent volume claims and get them in the bound state and get them visible in the Heketi API, it takes between 4 and 6 seconds, depending on is it brick multiplexing on or not. For brick multiplexing on, it is faster, off it's a bit slower. I'm still investigating why is that, but seeing that previous graph with memory consumption and with relation what Shekhar said about performances, I don't think it's a wise idea to use brick multiplexing off at all. I mean, it should be on, and that is what we have at the time. So this shows how long it takes, the orange graph, to get persistent volume claim created and mounted inside the pod. So it is around 5.2 seconds, and I see per one persistent volume claim, what is in my opinion very good. And this result can vary, for example, 100 seconds on another try, be faster or slower, but it is always in that range. I tested it across 5, 10 times, so that is a persistent result. And
So I'll go, they have questions.
yes, please.
Yeah.
Who?
You said 6 seconds, or is it 6,000 like the chart says?
Per volume, 6 seconds. Yeah. So if you request, if user requests persistent volume claim, it will get that claim created, and then on the storage side and mounted to inside the pod, and everything within these 6 seconds. That is what I have seen. And
Questions?
yeah, please. Yes, please.
Do you have a baseline for other types of storage?
That's a good question. Actually, I was testing, this was the SATA disk as a block devices for the CNS. I was testing on the Amazon with SSD devices and for the CNS storage, and the results are similar. So there is no, I didn't notice some big difference if I put SSD devices underlying for the CNS block devices in regard to this scalability. I mean, I/O performances probably will be better, but scalability in my tests were in the same range. So no problem. More questions? Okay. This is interesting thing, and maybe to trigger some discussion around. When I create 1,000 persistent volume claims, or when I request 1,000 persistent volume claims, then 1,000 Heketi volumes will be created inside the CNS cluster, and they are visible in Heketi CLI volume list. But at the same time, that is going to trigger and it will be visible 2,000 logical volumes on the node where the OpenShift CNS pod is running. So that could be a bit tricky for the systems if we decide to push more, because it will just pump the number of logical volumes visible on the OpenShift nodes, which are hosting CNS pods. And the situation at the time is user, in this case developer, is in the position and that is what we want, to create a persistent volume claim, but that is triggering in the chain on the other side, on the storage side, is triggering a root level action, creating the logical volume. And at the time, situation is like this. So 1,000 CNS volumes or Raketi volumes generate 2,000 logical volumes per OpenShift node hosting CNS pod. So that could be the problem. So what else? As I said, CNS pods are important pods. I really think it is not good idea to kill them and destroy them without some big reason. And so CNS pod. So next slide. And in next steps, we plan to do more testing with, for example, specific OpenShift applications like memory and like logging and metrics, and some work is already doing in that direction. And there is also the work we plan to do in regard with CNS block, what is a new feature, and additionally we plan to do scaling with CNS block and scaling and I/O results for these two tests. Brick multiplexing, in our opinion, brings improvements from the memory consumption point of view, so it is strongly recommended to use it. It doesn't bring problems with I/O tests. At least we were not able to locate them and to figure out is there a problem with that. And definitely, I think it is good to have it enabled all time, as it's by default. Yeah, I think that's the last slide. If there is any questions, here or later, there is one.
Thanks. I just wonder that with the brick multiplexing, how is it decided that how many bricks or which bricks will be managed by that single cluster FSD process?
I think it can be enabled by brick. Yeah.
So as of now, we just have only one process. Every bricks gets attached to that particular process. Now, if you talk from a technical perspective, there is a logic by which we determine whether one particular brick is compatible to be attached to another brick by looking at different volume options. We also did bring in one particular tunable in volume option, by which you can still decide that how many maximum number of bricks you can attach to a process, which I don't think that you have that data with that particular tunable. Yeah.
Yeah, there is one correction in the observations there, I guess. It said it uses one port for all the bricks. That's true for the listener port, which accepts the connection, but the data transfer still happens on multiple ports there, right?
Once the connection is made, then there are multiple ports, right?
Yes, yes. So basically, the individual data transfer happens on different sockets, basically. The port consumption is the same, but there is usually a confusion between the sockets and the port. So people would normally assume that it consumes only one socket for all the bricks over there. So that's not entirely true in the current model, I guess.
Okay, thanks, Raghavan.
Yeah, thanks. So you said, I mean, about why the creation of the volumes is slower when brick multiplexing is off. My
Yes.
guess would be that it's because it requires to bring up these additional processes and wait until they're ready.
I think so as well, but I didn't investigate that. And to be very honest, when I saw the results regarding the memory consumption, in my opinion, it doesn't make much sense to play with brick multiplexing off. I mean, if someone decide to go, it's possible, but I lost my motivation to, I mean, I can do that again if necessary, but it obviously shows in all tests it consumes less memory. It doesn't destroy I/O tests, so use brick multiplexing on, and it's faster as well in that sense of creation. Yeah, and I think with brick multiplexing, people will be able to pack more persistent volume claims per OpenShift node hosting CNS pods, actually for the CNS cluster. And I have tested show you for 1,000. And if you divide that, you will get the idea how, and that is what I'm seeing it as, for example, 500 or 300 or 100. That is following that direction of how fast they are created, these persistent volume claims. Michael mentioned his presentation. At the moment, we are also focusing on the delete time, and we'll also show these results soon. But at the moment, I think CNS creation time can, without any problems, get inside the CLIs what is offered by some other storage providers in the sense of scalability and how fast these persistent volumes can be delivered or will be delivered to the end user. Do you have more questions, guys? Okay, if there is no more questions, thank you for your attention. We enjoyed it.